Hey guys, it's Liz. So today I'm just going to go through some basic R code to show you how to read in data to R and just kind of get familiarized with the RStudio console, as well as just getting an introduction to using R. So for those of you that haven't used R before, R is a really cool open source software platform, basically. It's a code-based language that allows you to do statistical analysis and graphical representation of different forms of data. And it's really, really useful. And the fact that it's open source and free has meant that there's a huge community that's been building over the past decade. And a lot of documentation of previous code that's already been done. So you don't really have to reinvent the wheel in order to get started with R, which is pretty great. So today we're going to do some data visualization and just get started getting introduced to R. So with that, I'll go ahead and share my screen. All right, so this is Fisheries Management and Techniques Laboratory, Biology 696 at Kansas State University for the fall 2020 semester. And so basically, you guys can read this for your assignment yourself as you go through it, but a lot of fisheries managers use R to be able to assess fisheries populations, fish populations. And so one of the first tools that we use for that is length frequency histograms, where you literally just have a representation of the number of fish on the y-axis, and then along the x-axis you have different length groups. So these would be fish lengths in centimeters. And so, for example, for this fish length group at 16 centimeters, we have over 80, probably like 90 some fish that are 16 centimeters long. And so that's a length frequency histogram. Pretty easy to interpret, pretty straightforward. This semester, we're going to be working with some largemouth bass data from the Tallgrass Prairie National Preserve in Strong City, Kansas. And so for fisheries management labs every other year, my advisor, Dr. Keith Gitto, has been taking students out to the Tallgrass Preserve every other fall since 2020 and has been building up that data set, which is pretty cool. And so we're going to go ahead and use some of those data to evaluate length-weight relationships for tallgrass, the tallgrass bass populations. So next, let's see, I'm going to stop sharing for a second. So this is asking you to just go through, there's a file here, the tpnp.xls in Canvas, and you need to go ahead and follow through and do some of these length frequency histograms in Excel. Okay, so now I'm going to share my R code. All right, here we go. So welcome to RStudio. So first I want to orient you a little bit just to what you're seeing on the screen here. So up here where my cursor is waving around, this is the R script window. So this is where you're editing and writing all of your code. Down here is the console. And so when you enter lines of code up here, you then get the outputs, the computer telling you what it's doing and the results of those lines of code down here. And you'll see that it pops up. The console moves pretty quickly in R. And so there will be a lot of different lines of code that then get pumped out for outputs that we're going to be able to analyze. All right, now going up to the upper right-hand corner, we have our global environment. And so this is where we're going to see all of our databases and things like factors, so different variables for data sets will all be in this global environment up here. We also have this history tab, connections and tutorial, which are just different tools to allow you to see what you did in the past or to bring in connectivity of other data sets and things like that. Now, if we go down to the bottom right-hand corner, notice I can click and drag and move and adjust the various sizes of all of these panels. It's really customizable, which I love. So down here is going to be the files, packages, and plots console. And so I've got a bunch of different files that I could pull in from here. I've got, once we run code to generate a plot, it'll show up here, and then you can click on export, and you can export your plots to save them as JPEGs or other types of files. You can save them as like bitmap and other forms to be able, and like meta files to be able to export them. And then we have this tab called packages. And so this is my user library of all of the different R packages that I use on a regular basis and have downloaded. So these packages are basically little sets of code that you download that are publicly available online. You don't even need to go to an internet page to be able to download them. You can literally install them right here if you know their names within your R script, which is really great. And so these are all just sets of code that run different functions that someone has already put together and published their code to do different objectives in R, which is pretty cool that all of these things are made so readily available to everyone. So, okay, next up, we're going to look at some of the code that we have. So the first thing you need to do when you get into R is you need to set the working directory. And so the working directory is kind of like your homeroom. So we are telling the principal, R's brain, where to look for a particular student, where to go retrieve information about a particular student. And so the first thing we have to do is set the working directory. And so this is telling R where you want to have the data saved and where the data that you want to work with. And so we're going to work with the TPNP and flathead length weight data sets saved in my documents. So I'm going to go ahead and run my set working directory. So this is on my C drive within users. I use the Dropbox app, and then I've got a folder called fish management, and that's where I'm reading in from. So the first thing we're going to do is import the TPNP data from a CSV file and bring it in. And so we're going to run this line where it's reading the CSV file from that folder and creating a data frame called tpnp.df. And then this is just telling R what to do with the row names. And then we're going to go ahead and attach the variables to this data frame. And this attach function just allows you to call the names of variables from the data set specifically without having to use these little $signs. And so now if we do tpnp.df $pond name and use this with function where we have the name of this data frame, comma, interaction, which is a function. We are saying that we want the interaction between drainage and the factor pond number. And so you use this with function to create a variable that's combining the information for drainage and for pond number into a new variable called pond name. So we are assigning it the name pond name. The $sign means that the new variable, or excuse me, the $sign means that the new variable with will be automatically concatenated to the end of the data set. And so we run that. Then you'll notice that there are all of these $signs and green text. And so that is a form of annotating your data. So we annotate our code in order to write notes to ourselves or to anyone else that will use this code so that they understand what's happening. And so we do this annotation in order to make notes for ourselves so that we can come back later to our data sets and figure out what the heck is going on. All right, so we're going to go ahead and now we're going to go ahead and run this next line of code, which is the head function. The head function automatically yields the first 6 rows of the new data set. So if we look down here, we've got the drainage, pond number, pond name, date, gear, species, length, and pond name, that new variable we just created. And we see that we are only getting the first 6 rows. And this function is primarily to just give you a sense of the structure of the data set without having to see the whole darn thing. So next up, we need to use this attach function that has to be called again because we want to change the degrees freedom for the first times we used attach. So we're doing that. So this red text right here, the following objects are masked, just is telling you that some of the variables are the same. So now we're going to create a data frame from a subset of all the data for just Gas House Pond 1. And so we're using the which function within that. And so the new data frame will be called gh1.df. We use this little arrow to assign it. So that's the arrow in R is usually used to rename things or assign things, to do some kind of function for us. And so we're pulling from this tpnp.df original data frame and doing which, and it's telling R that within that data frame to go into the pond name category and just pull out the stuff that matches Gas House 1 because we don't want the other ponds data. So we're going to go ahead and do that. So we've subsetted it. Now we're going to make a length frequency histogram for largemouth bass from Gas House Pond 1. And so the function hist makes a simple histogram. And then if you do gh1.df by length, that'll pull the length variable. And then this xlab and ylab in the quotations define the labels. And then the xlim and breaks are just, these are defining the limits of the different plots. So here we go. Now, if you avert your attention over to the bottom right-hand corner, you see that we have this nice length frequency histogram. So on the x-axis, we have total length in millimeters, and on the y-axis, we have the frequency. So around 230 millimeters total length, we have almost 25 individuals versus out here at 500 or 600 millimeters, we only have maybe one individual. So that's a length frequency histogram. So now we're going to do an XY scatter plot for length and weight. So length weight relationships are really important for fisheries managers. It gives us a sense of the condition or the general health of different species. And it gives us a method by which we can compare the fish in one location to fish in a different population or different body of water. So it's a method of comparison, and it gives us some ideas about one of the dynamic rate functions, which is growth. And so I don't know if you guys have been exposed to this before, but in lecture, we talked about the 3 dynamic rate functions of fisheries, which are growth, recruitment, and mortality. So how quickly are your fish growing? How many of them are recruiting to the population? So not only how many are produced each year, but how many survive, like of the young of years survive to become age 1 fish. And then mortality. So how many fish die each year from natural causes and then from angling mortality. Both of those components are really important to understand when managing a fishery. All right, so now that I've explained that, let's go ahead and create an XY scatter plot. Oh, sorry, we don't need to change that directory. So now we're going to read that table in, use the attach function, use the head function to see these first few right there. Now we're going to run a simple XY scatter plot. Boom. Okay, cool. So now we have, we see this exponential relationship where as you increase in total length, you increase your weight for catfish. And that makes sense, right? That's pretty intuitive. Like bigger fish are going to weigh more, right? So if you had the opposite pattern, you'd know that something's fishy and something's wrong. All right. Next up, we're going to do a log transformation of total length and weight. And so to do this, we just do flathead by log TL. And so this is just doing the log 10 transformation of this variable total length. Same thing with weight. We're going to attach the flatheads. We'll plot this, do AB line, and that gives you log transform total length and weight, which kind of normalizes that relationship. And this is one way to visualize the data. Transform data are sometimes difficult to make sense of though. And so we need to keep that in mind, that when you transform those data to normalize them to fit a line like that, that you lose some of the variation, which interpreting that variation is important. Okay, so one way to deal with that is to transform the axes and then to plot the raw data onto them. And so the argument log can transform either the x, the y, or xy axes. So what we're going to go ahead and do and run this plot, and then notice we've got columns black. This is just telling you what size dots you want, and then log is xy. Boom. Okay, so now we want to run a simple linear regression. And so we're going to go ahead and run this M1 is just assigning it to model 1. This little function called LM is just a linear model, like a simple linear model. And so we're taking a linear model of the log transformed weight by the log transformed total length. And then this summary M1 is just going to give us an output of like the ANOVA table and F statistics, things like that. So we'll go ahead and run that. Bingo. Okay, so now look down here in the console and see we've got our formula here for the regression equation, our residuals, our coefficients, so our intercept estimate, and then our total length estimate, our standard errors, t-values, and p-values. We've got our residual standard error on 344 degrees of freedom, the multiple r squared and the adjusted r squared values, and your F statistic and p-value, which is pretty groovy. And so for your assignment, you're going to produce a length weight figure for 2 different fish species. So you can go back through on Canvas in that folder and find green sunfish, one of those, 1 or 2 of those species, and go ahead and make plots like these. And then make sure that you provide the r squared value, the slopes, and the y-intercepts for your regression equation. Next up, we're going to do some comparing of means. So we're going to talk about students' t-tests. So we're going to import this Eldorado Bass data set and read in that table. We're going to need this library car data. So I'm going to go ahead and attach those variables. I'm going to subset them out by to be able to compare the means using a t-test, assuming equal variances. So we're subsetting by treatment. So there's a variable, the independent variable that we're manipulating here is whether or not there's water willow habitat. And so we're going to do one that's called willow, one called no willow. Now we're going to calculate the mean and standard deviation. That's what this mean and SD function does. And now we're going to make a box plot to compare those two. So boom, there's a box plot of our CPUE, which is catch per unit effort. The higher the catch per unit effort, the more fish were caught per net night hour or per hour of electrofishing. So it's kind of like a rate of how much effort you put in compared to how many fish you caught. And that gives us a sense of densities or catch rates. So, okay, so we've got this nifty little box plot, and now finally we're going to test that the variances are equal among groups, because one of the assumptions of a t-test is that homogeneity of variances among treatments will be this equal. And so, there is homogeneity of variances. Okay, so the p-value will be 0.05 alpha. If the variance assumption is not met, it'll be greater than 0.05 alpha. If it is met, it'll be equal to or less than, right? Good. Okay, so now we're going to go ahead and run this bar test. Pew! Okay, so this initial assumption was not met, right? So because we failed to meet this this first test, the F test to compare the variances, then we ran a t-test comparing the mean CPUE of age 0 rather than the full distributions. And so then if we do the means, we see the mean of X was 46.83, the mean of Y was 27.3333. And so there was a significant difference between the willow and no water willow treatments. So having water willow significantly increased the catch rates, the CPUE of the largemouth bass in that sample. All right, and so now going back to your assignment, we did just a little bit of linear regression just now when we did that LM function. That's basically what we were doing. And so I want you to go through and review this linear regression. Here are just some examples of regression lines showing different slopes and intercepts. Remember that the closer the data pairs are to the regression line, so the closer these points are to the line, the higher the coefficient of correlation, or R. The highest possible R value is 1.0, indicating that data pairs are in a straight line. The lower the R value, the more variability in the regression line. So if you have two regressions with the same correlation coefficient, the one with more data pairs has a lower probability level than the one with fewer pairs. So figure 3 kind of demonstrates this concept. So the R value is actually the square root of the coefficient of determination, so R squared. So the R squared value indicates the percent of variability in the dependent variable that is explained by changes in the independent variable. So that's why we pay attention to R squared. So yeah, check out figure 3 is just PSD, proportional stock density versus relative weight. We see that relationship reflected in the R values and the P values. All right, next up, we're going to do this exercise with largemouth bass growth. And so it's going to give you these biomass and mean length at annulus 3 estimates. So these are just length and then total community biomass estimates for this species. And so I want you to go ahead on the graph below and plot that relationship and label your axes. So I went ahead and I found the statistics for this relationship to be these values right here. And note that the correlation coefficient and the slope indicate a positive or a negative slope. And so now from that, you can put these values in for the regression equation using this general formula right here, right? So you can go ahead and do that. And so now it says, once you have the regression equation, you can predict the likely growth of largemouth bass if you know the biomass. So if the largemouth bass biomass is 52 kilograms per hectare, what would you expect is the mean length of bass at annulus 3? And so you can plot the regression line and then go through those predicted pairs. And an important note is to not extend your regression line beyond your observed data pairs. That would be over extrapolating, and we tend to frown upon that because we don't have values in that range. And so that's generally a no-no in statistics. And so now that we have a basic understanding of how linear regression works, we're going to use RStudio to generate those regression plots. So I talked about how you're going to need to make two different species, plots for two different species with total length on the x-axis and wet mass on the y-axis. And so you're going to go ahead and paste your graphs in there, show your regression graphs, and then we'll move on. So finally, we're going to do comparing means for a t-test. So it's often necessary to compare the mean conditions between or among groups of samples. And so we just saw those data in the R code about the treatments between bass with water willow present and water willow absent. And so if you go back to your console output, the mean values for each of those groups and the standard deviations were there. But we're going to learn here how to calculate those by hand so you understand some of the magic working underneath the hood. So on average, there's a greater number of age 0 largemouth bass in the coves with water willow present. But we need to know how confident we are that this difference is biologically important, and that depends on your precision or variation in the data around this mean value. So if the values are very precise, if the means are precise, we can feel confident that even with the small difference, the groups is relevant. But if the measurements are not precise, then a greater difference between the groups, a stronger significance is necessary for us to have confidence. And so here's how you calculate variance. So variance is represented as S squared, is n times the sum of x squared minus the sum of x squared over n times n minus 1, whereas the standard deviation is the square root of n sum of x squared minus sum of x squared divided by n times n minus 1. You guys should look up online if those are new concepts for you, because I'm not going to spend a bunch of time here talking about it. All right, so a student's t-test is used to test the null hypothesis that the means of two groups are equal. And so if we reject this hypothesis, the null hypothesis, then we're confident that there's a difference between groups. So before we run the t-test in RStudio, we'll first graph our data. So you've already graphed it, and we're going to use the average and standard deviation. We use the box plot function, and then go ahead and give us the p-value for this test and tell me what it tells us about the success of water willow plantings in reservoirs. Will it help largemouth bass or will it not provide an effect? And then produce that figure using the code provided at the end of the R code. All right, I'm going to stop sharing. That was the end of Lab 1. If you have any questions, feel free to email me at earenner@ksu.edu. And with that, have a good evening, and thanks for watching.